Hello and welcome to Unit 6, Lecture C. We're going to talk about some of the specific groups that you find on the periodic table and some of their basic properties and wrap up this unit. Okay, so remember that the groups are the ones that go vertically up and down. They tend to ask you for the trends as you go down a group, so from top to bottom. Most of these you can find on reference table S. So the radius, the ionization energy, and the electronegativities you can find on table S. Pick groups to look at the trends and just look up the numbers. Again, you have to be careful with groups because you're going to skip. So group 1 is lithium, sodium, potassium, etc. If they want metals, try to use group 1 or 2. If they want nonmetals, use group 17, the halogens. So fluorine, chlorine, bromine, they'll give you the best trends. Memorize or look up that the covalent radius increases as you go down a group because there are more principal energy levels. The ionization energy, or how much energy it takes to remove the outermost electron, decreases as you go down a group because the electrons are farther from the nucleus and there are more electrons shielding the outermost one from the positive nucleus. Electronegativity also decreases for the same reason. They're farther away and there's bigger shielding effect from the electrons. So electronegativity is how well they attract electrons. The more electrons between the nucleus and the outside, the harder it is for it to attract electrons. And metallic properties increase as you go down a group. That one you have to memorize. Basically, to be very metallic, you lose electrons easily. The farther down the group you go, the lower the ionization energy is, the easier it is to lose your electron, and therefore the more metallic you become. Okay, group 1 and 2 you need to memorize the names of. Group 1 are the alkali metals. Group 2 are the alkaline earth metals. I've written them on the periodic table already. If you haven't already written those names in, you probably should do that now. Remember that hydrogen, although he is lined up here with the alkali metals, he's not. There's this gap here. Hydrogen is definitely a nonmetal. He makes positive 1 ions and negative 1 ions. So some tables put him here with the metals, some over here right next to helium in period 1 with the halogens, because the halogens all make negative 1 ions. Our tables line him up over to the left because of his electron configuration. He has 1 valence electron, so he's lined up with the rest of group 1, all with 1 valence electron. So group 1, 1 valence electron, group 2, 2 valence electrons. That means group 1 is going to lose 1 electron and become plus 1 ions. Group 2 are going to lose 2 electrons to become plus 2 ions. This way they can look like the closest noble gases. They all have low ionization energies and low electronegativities. They're very metallic. They're very reactive. You are never going to find them in nature in their pure form. The group 1 metals are the ones that when you throw them in water burn and explode. So sodium and potassium. In compounds, when we make solutions with them, they tend to be white compounds. They tend to make clear solutions, and always in compounds in nature. So they have to do something to extract out the pure forms. Only their valence electrons are involved in chemical reactions, and that will be important when we talk about transition metals later. The activity increases as you go down a group. Group 1 always more reactive than group 2. So a lot of times a test question will ask you to compare which one is most reactive. You're looking for the metal with the lowest ionization energy. If they're in the same period, the group 1 will always be more reactive than the group 2. We're going to skip the transition metals for now and go right over to group 13 because 1, 2, and then 13 through 18 show the best trends across the periodic table, and then the transition metals are a little bit different. Group 13, 3 valence electrons. They all make plus 3 ions. That's the most common oxidation state for them. It starts with boron. The state's not going to ask you for the name of that group. Group 14, 4 valence electrons. They're right in the middle. They're either going to lose 4 or gain 4 if they want to look like noble gases. So they kind of can be either types of ions, but for the most part, later on when we talk about bonding, they're going to end up sharing their electrons instead. So they tend to neither gain nor lose electrons, but you're going to see this beautiful trend of going from a nonmetal to a metal. So if you want to show that the elements get more metallic as you go down a group, and we take a look at group 14, we start with carbon. So you're familiar with carbon. black, dull, brittle, solid. Silicon and germanium are both metalloids, so that's more metallic than carbon. They start to get silver and shiny, but they're still brittle. And then SN is tin and PB is lead. So tin and lead both definitely metallic, and you are familiar with tin and lead being metals. So we see this beautiful trend of going from nonmetals to metals as we go down group 14. Group 15 on your periodic table, I'll have 5 valence electrons. It starts with nitrogen. They will tend to gain 3 electrons if they're going to make ions and make -3 ions, so they can look like noble gases. We are also going to see that trend from non-metal to metal as you go down that group, but this misses the metal that it ends with, and I don't think you're as familiar with that as you are with tin and lead from group 14. Typically with nonmetals, the elements to the top are the most reactive. So in metals, they get more reactive as you go down, and in nonmetals, they tend to be more reactive as you go up. Group 15 has an exception to that because phosphorus will actually be more reactive than nitrogen. Nitrogen is special. He is very unreactive. He's diatomic. So we learned that before. That means that there's 2 nitrogens in every one molecule. So in the atmosphere, 78% of what you're breathing is nitrogen. Those 2 nitrogens hold onto each other with what we call a triple bond. So they're going to share 3 sets of electrons, 3 orbitals overlap, and in order for nitrogen to react, you actually have to break all 3 of these bonds to get it into 2 separate pieces. So it makes nitrogen less reactive than other elements. So it is actually less reactive than the phosphorus, but then phosphorus will be more reactive than the other nonmetals in the group. Group 16 starts with oxygen. Oxygen also diatomic, but oxygen, on the other hand, is highly reactive. When we talk about reduction oxidation reactions, it's all going to be based on the fact that oxygen tends to make all kinds of compounds. It combines with most elements, so it's going to be the most abundant element in the crust. When you look at our table of polyatomic ions, you find oxygen in almost all of them. Sulfur below oxygen, less reactive, solid, brittle yellow. Most of you are familiar with this smell of like sulfur from our hydrogen sulfide or sulfur dioxide gases. And polonium is the first radioactive element that you're going to run into if you're going in order of atomic number on your periodic table. There's no stable form of it, and we know that because its mass is in parentheses. Group 17, the halogens are kind of important. 7 valence electrons. They're going to be the most reactive of the nonmetals. Fluorine is the most reactive because he is the one with the highest electronegativity. Very easy for him to gain his 1 electron. You're never going to find fluorine in nature in its pure form. I don't think you'll find any of these in nature in their pure form. They're always going to be in compounds. They're that reactive. They very readily make -1 ions. Fluorine is the one that all electronegativities are based on. He has an electronegativity of 4.0. We see the trend of going from a gas to a solid down the halogens. As they get heavier, they're going to clump up more and go from gases to solids. So the bigger and heavier they get, the more likely they are to be solids. Even iodine, though, sublimates at room temperature. We remember that from our phases of matter unit. So although he's a solid, he doesn't hold on to each other really, really well, and they are very reactive. They're all poisonous. They're all used as disinfectants. Noble gases are inert. Inert means they are unreactive. They do not make compounds. We can force some of the larger ones to make compounds with fluorine, and sometimes if they can get high enough pressures and temperatures now, they said they've made some with oxygen as well, but it has to be a super reactive nonmetal and really artificial conditions. They're not going to make any compounds under normal conditions here on Earth. They have extremely high ionization energies because having those full valence energy levels is the most stable, so it takes a lot of energy to get any of those electrons off. That's why you need the high temperatures and pressures to get them to react. They are considered molecules, only one atom, because they have those full valence energy levels and are stable. And so we call them monatomic molecules, mono meaning one. So only one piece, if I just have a helium, just one atom, he's considered a molecule. The transition metals aren't just one group. They're going to be groups 3 through 12 on your periodic table. And again, they should already be labeled on your table or labeled when I labeled your periodic table before. What makes them different and special is that they don't just lose electrons from their outermost energy level, not just from s&p orbitals. The transition metals can also lose electrons from their d sublevels. So this is why they all tend to have the same number of valence electrons, 2 or 1. They tend to gain electrons and lose electrons from that d sublevel as well. It also lets them have more than one oxidation state. So if we look at our periodic table, the group 1s only make +1 ions, the group 2s only make +2 ions. But here in the transition metals, we get things like chromium that can be different, +2, +3, +6. Manganese has a number of positive oxidation states that it could possibly be. Most of them have more than one, and that's because they're not just going to lose their valence electrons, but they're also going to lose some of those d sublevel inner electrons. All of the elements from groups 3 through 12, their d sublevel electrons are being filled in. Those can be gained or lost as well to make ions, and so we get more than one positive oxidation state. So if we're looking at examples of names, this is where we get the stock system from. Remember that this Roman numeral tells you the charge. It does not tell you how many pieces, it tells you the charge. So this is telling you you have copper +1. And we're going to put that together with chlorine, which is -1. This Roman numeral says I have copper +2. And I'm going to put that together with chlorine -1. We're making compounds so that the total is 0. So copper 1 chloride is CuCl, and copper 2 chloride is CuCl2. Notice that it's not 2 coppers that I have. I only have 1 copper. It's 2 chlorines to get my total charge to be 0. There are no transition metals in periods 1, 2, or 3. They don't start until period 4. And this is one of the key characteristics of them. This is where we get all of our colored compounds from. The group 1 and 2 metals, clear solutions, white compounds. The transition metals are where we're going to get all of our pretty colors. Think of the copper and the copper sulfate that we've used in lab and that pretty brilliant blue color. It's because of the transition metals. Our gemstones are all the pretty colors they are because of the transition metals. As we go across the periods, remember periods are the horizontal groups that are going from left to right. There's a certain number of trends you're supposed to know. Again, ionization energy, electronegativity on reference table F. Ionization energy, how much energy it takes to remove the outermost electrons. It increases because the number of protons in the nucleus increases, holding the electrons better. Electronegativity, how well you gain electrons, also increases for the same reason. There's more protons in the nucleus to pull on the electrons with. You're going to see this trend from very active metals to regular metals to nonmetals to noble gases as you go across any of the periods. If we're looking for trends in a period, stick to periods 2 and 3 to look for trends. You avoid the transition metals that way, and period 1 is just too small. It only contains hydrogen and helium. The valence electrons, you can just look at your periodic table and see the valence electrons increase. We go from making positive ions to negative ions. We end at the noble gases making no ions at all or zeros for their oxidation states. The A groups, that's groups 1, 2, and then 13 through 18, the representative groups, so ignoring the transition metals, we see a decrease in metallic properties as you go from left to right. All of these trends kind of level out in the transition metals, so we tend to ignore them when we're looking for general trends. All right, hopefully your periodic table is now a very useful, helpful tool and will help you in all the rest of your chemistry work.